More than 1 billion tons of agricultural waste are left behind each year in the wake of the impressive achievements of modern agriculture. As environmental pollution becomes increasingly evident and biological waste grows faster than traditional processing capacities, agricultural byproduct recycling has emerged as a strategic shift, transforming production leftovers into raw materials for new value chains. Alongside advances in modern processing technologies, hundreds of millions of tons of agricultural residues have entered the race to create sustainable materials and the green products of the future. Today, join Agriculture Insight as we explore how farmers around the world are turning waste into green profits worth billions of dollars through recycling innovations you may never have imagined. All will be revealed in this video. Eating a banana means throwing away the peel. That's obvious. But did you know that in many tropical countries, especially the Philippines and India, nothing from this zero-waste plant is discarded, not even the trunk? What was once cut down and left behind after each harvest is now collected, stripped into fiber, and recycled into high-value natural materials, generating tens of millions of US dollars each year for local communities. In the Philippines, the cradle of the global banana fiber industry, the Abaca banana is cultivated exclusively for fiber across hundreds of thousands of hectares, providing livelihoods for more than 1 million farmers and rural workers. Each year, this fiber brings in over 100 million USD for the Philippines and is recognized worldwide as one of the most durable, water-resistant, and strategically valuable natural fibers in the world. To produce natural banana fiber, the first step begins right in the field. After the banana bunches are harvested, the trunk is immediately cut down while the fiber content is at its optimal quality. A single decisive and precise cut is enough to bring down a banana trunk weighing dozens of kilograms. No machine can replace the hands and experience of farmers at this stage, as even a slight mistake in timing or cutting angle can significantly reduce the quality of the fiber obtained. After being cut down, the entire banana trunk is quickly loaded onto trucks and transported to a pre-processing facility near the field as fast as possible to prevent moisture loss and fiber oxidation. At this stage, the banana trunk is split lengthwise and peeled into individual sheaths. This is a critical step that directly determines the length and uniformity of the fiber, requiring steady hand control and practical experience. Ideally, the outer sheaths, where the cellulose fiber bundles are fully developed, yield the longest, strongest fibers with the least impurities. Farmers use specialized knives to carefully separate each layer along the natural fiber grain, avoiding damage or breakage to the fiber bundles inside. Despite modern tools, this step remains difficult to automate, as variations in trunk thickness and fiber structure still require human judgment. Each banana sheath is fed through a mechanical press or a manual stripping table to remove the soft pulp, leaving behind long bundles of cellulose fibers. Steady hand movements and precisely controlled pressure prevent the fibers from breaking, producing rough fiber strands with a characteristic ivory color. In practice, this work is far from easy, as the worker's sense of pressure combined with a consistent rhythm is a skill that often takes years for newcomers to master. After several hours of continuous processing, the result is bundles of raw fibers free of sap and retaining their full length, but still high in moisture and prone to discoloration if not washed and treated promptly. The raw fibers are then washed repeatedly with clean water, sometimes combined with mild biological enzymes to remove sap and impurities without damaging the fiber structure. Some facilities may use warm water to improve cleaning efficiency, or for fibers intended for paper production and coarse materials, apply stronger heat treatment to shorten processing time and reduce costs. Finally, the fibers are dried under natural sunlight or at low temperatures until they reach standard moisture levels, a process that typically takes at least 2 days. In major banana-growing countries, such as the Philippines, India, and Indonesia, banana fibers are traditionally sun-dried on bamboo racks or raised wooden frames under natural sunlight, allowing the fibers to dry evenly while maintaining their light color and strength. Once dried, the banana fibers become lightweight, durable, and flexible, ready to move on to sorting, spinning, and industrial production stages. Tens of thousands of tons of banana fiber are collected and sent to industrial textile mills and fiber processing facilities, where it is determined whether they will become fabric, rope, or natural mats. Once inside the factory, raw banana fiber must undergo the most fundamental and critical step, carding. Here, fiber bundles are loosened, straightened, and aligned in parallel, while short fibers, broken strands, and remaining impurities are removed. This process standardizes fiber length, fineness, and uniformity, creating a solid technical foundation for the subsequent spinning and weaving stages. After carding, the fibers are fed into the spinning system, where they are twisted under tightly controlled tension and speed. In actual production, banana fiber is rarely used in its 100% form, but is commonly blended with cotton, linen, or other bio-based fibers to enhance softness, strength, and weavability, meeting the demands of industrial manufacturing. The result is stable yarn wound into spools, ready for weaving, carpet making, or the production of finished textile products. Depending on the intended use, the yarn is fed into shuttle looms, knitting machines, or braiding machines to produce fabrics, bags, mats, or technical materials. Compared to cotton, this material stands out for its higher tensile strength, but requires blending to improve softness. When compared with jute, banana fiber is lighter and more flexible, allowing it to be used in products with higher aesthetic requirements. In packaging and interior applications, its load-bearing capacity and stability in humid environments give it an advantage over many other plant-based fibers. In sustainable fashion, it is seen as an intermediate option, balancing performance and environmental impact. In terms of cost, a garment made from banana fiber or banana-blended yarn currently sells for about 20 to 40% more than a standard cotton garment, due to higher collection and processing costs and the still limited scale of production. This remains the main barrier preventing banana fiber from becoming mainstream, as supply chains are still in the process of expansion and optimization. Each year, hundreds of millions of tons of banana trunks are reused instead of being burned, helping to reduce emissions by 20 to 30% in countries where bananas are a major crop, easing environmental pressure and turning agricultural byproducts into part of the solution for a global green economy. According to the United Nations, more than 400 million tons of plastic are discarded worldwide each year, much of it persisting in the environment for hundreds of years, forcing humanity to seek solutions based on natural materials as practical and necessary alternatives. Among zero-waste materials, bamboo has emerged as a leading choice thanks to its rapid renewability, high durability, and low environmental impact. And one of the most talked about household items today is the bamboo toothbrush. To produce toothbrush handles that meet quality standards, bamboo selected must be 3 to 5 years old, when the fiber structure has fully developed and reached its highest stability. After harvesting, the bamboo is transported to the factory and cut into moderately long sections suitable for preliminary processing. These sections are then split lengthwise into uniform billets with consistent cross-sections. The entire cutting and splitting process is automated using industrial saws, splitting machines, and conveyor systems, ensuring high precision, stable output, and reduced material waste. Next, the bamboo is soaked in a mild biological solution to remove natural starch and sugars, preventing mold and insect infestation. This step is critical to the product's durability and safety in use. After drying and reaching the required moisture level, the bamboo is shaped into handles. Each bamboo blank is fed into the machine and cut, contoured, and rounded according to preset molds, forming ergonomic handle shapes that fit comfortably in the user's hand and meet everyday use standards. Advances in CNC machines and automated sanding technology make this process more precise, consistent, and efficient, while also reducing material waste. The head of the handle is drilled with small holes in a standardized layout, preparing it for the bristle insertion stage. This step is carried out using high-speed CNC drilling machines capable of producing hundreds of holes per minute with near-perfect precision. Thanks to advanced automated control systems and sensors, the position and depth of each hole are fully synchronized, ensuring consistent quality at industrial scale. The next step is bristle insertion. Despite being an environmentally friendly product, the bristles of bamboo toothbrushes are still primarily made from nylon, a limitation that has yet to be fully replaced. This is because nylon currently offers the best combination of durability, elasticity, and safety for gums according to dental standards. However, compared to conventional plastic toothbrushes, bamboo handles are biodegradable, significantly reducing the amount of plastic waste remaining after use. After bristle insertion, an automated trimming and polishing system evens out the bristle length and rounds the tips, ensuring a smooth surface and safe contact with the gums in accordance with dental standards. Once completed, the toothbrush is printed with brand logos using automated inkjet printing or laser engraving, ensuring clear, consistent, and long-lasting markings on the bamboo surface. Finally, the toothbrushes are sterilized and inspected for bristle retention and surface finish before being packaged in paper-based or recycled materials, minimizing the use of plastic. Following the wave of efforts to reduce plastic waste, paper bags, one of the most promising alternatives to single-use plastic bags, have emerged as a solution that cannot be ignored. Since around 2015, when many countries began restricting and taxing plastic bags, the shift toward paper-based packaging has accelerated rapidly, pushing the global paper bag market beyond $7 billion annually. Concentrated mainly in the United States, the European Union, and Japan, while helping many countries cut approximately 10 to 20% of single-use bag waste. So how are these revolutionary bags actually produced? Let's start with the most fundamental raw material of paper bags: plantation wood. In the past, the paper industry relied heavily on natural forests. But to ensure sustainability and control emissions, today's wood mainly comes from managed plantations such as eucalyptus, pine, and acacia. In the United States, the world's leading producer and consumer of paper packaging, the paper industry uses more than 400 million tons of plantation wood each year, with carefully controlled regeneration cycles. After harvesting, the wood is transported to the mill, debarked, chipped into small pieces, and cleaned before entering deeper processing stages. This step standardizes material size and removes impurities from the very beginning. But the key factor that truly makes paper bags a sustainable solution lies in their raw material source: recycled paper. Used paper is collected, sorted, and reprocessed, helping to significantly reduce the demand for virgin wood, while also cutting down energy and water consumption compared to producing new paper. In many developed countries, 40 to 60% of paper used for packaging comes from recycled sources. In addition, some factories also incorporate agricultural byproducts such as bagasse or straw, further expanding the value chain for the circular economy. Once the raw material supply is ready, pulping, the most important stage of the entire process, officially begins. Wood, recycled paper, and byproducts are fed into large pulping tanks, where they are treated through a combination of mechanical processing and mild chemical treatment to separate the cellulose fibers. For craft paper, the goal is not to produce smooth white paper, but to preserve long, strong fibers, which are the key factor behind the superior strength of paper bags. This process requires strict control of temperature, pressure, and time to achieve uniform fiber quality. The pulp is then washed and filtered multiple times to remove lignin, impurities, and residual chemicals remaining from the pulping stage. Once the required level of cleanliness is achieved, the pulp is diluted with a large amount of water to ensure even fiber distribution and then spread uniformly onto a moving mesh system. As the pulp travels along the mesh, water is gradually drained away through gravity and suction. During this process, the cellulose fibers naturally interlock and bond with one another, forming a continuous thin sheet of paper that serves as the foundation for further processing. Next, the paper sheet passes through a series of pressing rollers and drying chambers, where excess moisture is gradually removed until the moisture content is reduced to below 8 to 10%. During the pressing stage, mechanical pressure helps expel additional water while improving fiber bonding and paper density. The drying process is carefully controlled at temperatures typically ranging from 90 to 120 degrees Celsius, which is sufficient to fully dry the paper without damaging or weakening the fiber structure. Precise control of heat and airflow ensures consistent paper quality and prevents brittleness. Finally, the dried paper is wound into large craft paper rolls, making it ready to be transported to the bag forming stage. The large craft paper rolls are then fed into an automated paper bag production line, where they are cut according to preset molds that match different bag sizes and designs. The paper is divided into individual sheets, which then go through a series of steps including folding, side forming, bottom gluing, and handle attachment. At this stage, bio-based adhesives or safe industrial glues are used to ensure strength and durability while minimizing negative impacts on the environment and human health. Compared to plastic bags, which can persist in the environment for 200 to 500 years, paper bags decompose up to 50 times faster, typically taking no more than about 6 months under natural conditions. In addition, paper bags can be recycled 5 to 7 times, significantly reducing long-term waste accumulation and easing pollution pressure on both land and oceans. However, due to higher production costs, usually 2 to 3 times that of plastic bags, paper bags have not yet been able to fully replace single-use plastic bags, at least for the next decade. What about you? Would you choose paper bags for the sake of the environment or continue using plastic bags for their immediate convenience? For green consumers and those who favor environmentally friendly products, the Luffa sponge has long become a natural alternative to convenient but polluting plastic sponges. From just a mature Luffa gourd, people can create sponges made 100% from natural cellulose fibers, free from microplastics and chemicals, and fully biodegradable after use. India is considered a pioneer in the cultivation and commercialization of Luffa sponges, long before this product spread to the United States, Europe, and other green consumer markets. To make sponges, Luffa gourds are not harvested while still young like food crops, but are left to fully mature on the vine. When the outer skin gradually turns yellow-brown, signaling that the internal fibers have fully developed, farmers harvest the gourds to ensure optimal fiber strength. After harvesting, the entire gourd is peeled to remove the outer skin, leaving only the natural Luffa fibers inside. These fibers are then thoroughly washed multiple times with water to remove sap, seeds, and remaining impurities, and are sun-dried naturally for about 7 to 14 days until completely dry. Once the moisture content is reduced to the required level, The fiber structure becomes lightweight, strong, and elastic, making it ready for the shaping and finishing stages. At production workshops, dried loofah fibers are cut into various shapes such as dishwashing pads, bath sponges, or skincare pads, then edge-stitched or compression molded to enhance durability and aesthetic appeal. Some products are also treated with hot water or lightly steamed to ensure hygiene before packaging. In many Asian countries where loofah is commonly grown, such as India, Vietnam, China, and South Korea, small and medium-scale loofah sponge production models can generate between USD 500 and USD 2,000 per month for households or local businesses. This is not only a low-cost and accessible business model, but also one that creates jobs in rural areas, transforms agricultural byproducts into sustainable value, and connects traditional production with global green consumer demand. Sisal is primarily cultivated in tropical and subtropical regions, with over 90% of global sisal production coming from Africa and South America. Throughout the 20th century, sisal played a significant role in international trade and was often referred to as green gold, at times serving as a major source of national income for countries such as Tanzania, Kenya, and Brazil. Sisal fiber is one of the most durable natural fibers ever used by humans. Before the advent of nylon, sisal was known as the king of ropes, widely used on ships around the world. With its high resistance to abrasion, exceptional tensile strength, and the ability to biodegrade 100%, sisal remains highly relevant today. And looking ahead, sisal is increasingly viewed as a natural alternative to synthetic plastics, helping shape the future of the green economy and sustainable materials. At the opposite end of the spectrum lies Lotus fiber. Unlike sisal, which is produced in hundreds of thousands of tons each year, Lotus silk exists in extremely limited quantities, as every strand must be hand-extracted from fresh lotus stems. To produce a single lotus silk scarf, between 7,000 and 10,000 lotus stems are required, and today only a few countries, including Myanmar, Vietnam, and India, still preserve this technique. This rarity is what gives lotus silk its value, often priced many times higher than traditional silk, and elevates it as a symbol of refined craftsmanship and cultural heritage. Now, let us explore one of the world's leading sisal-producing countries. In northern Tanzania, around the regions of Tanga and Morogoro, where rainfall lasts for only 3 to 4 months a year, sisal has not merely survived, but has dominated the agricultural landscape for more than a century. Sisal is typically planted at the beginning of the rainy season in March on gently sloping land where water does not stagnate, yet retains enough moisture for young plants to establish themselves. Seedlings are planted directly into the soil, spaced at approximately 1 meter apart, allowing their long, thick leaves to develop to full capacity. During the first 2 to 3 years, sisal requires very little intensive care. Thanks to a root system that penetrates several meters deep and a natural water storage mechanism within its leaves, the plant can thrive with annual rainfall of around 700 millimeters, significantly lower than that required by most industrial crops. It is precisely this paradox, minimal care combined with long-term productivity, that makes sisal an ideal crop for semi-arid agricultural regions. Have you ever noticed how sisal looks remarkably similar to a plant commonly used to make spirits? In fact, sisal belongs to the same agave family as the plants used to produce tequila and mezcal. However, while agave grown for spirits is cultivated to harvest the sugar-rich core at its center, sisal follows an entirely different path. It is grown to extract fiber from its leaves. This fundamental difference shapes every aspect of how sisal is cultivated and harvested. After approximately 3 years of growth, sisal enters its harvesting phase. The plant is not cut down. Instead, it is harvested repeatedly in cycles, a process that can continue for nearly 10 years. During each harvest, workers cut only the outer, mature leaves, where fiber concentration is at its highest. The central core and young inner leaves are left intact, allowing the plant to continue growing. Sisal leaves are cut close to the base using specialized knives. A harvest-ready leaf is typically over 1 meter long, thick and rigid, and heavy with moisture, requiring a firm, decisive cut to avoid damaging the fibers inside. Over its lifetime, a single sisal plant can produce more than 200 leaves, though only a portion is taken during each harvest to prevent exhausting the plant. Once cut, the leaves are laid out directly in the field, where overly young or damaged leaves are removed. Leaves that meet quality standards are then bundled uniformly, prepared for the next stage of the production chain. On average, a single worker can harvest more than 1 ton of sisal leaves per day. And on large plantations, total daily harvests can reach tens of tons. When sisal leaves enter the factory, the fiber extraction process begins immediately and runs continuously. The leaves are placed parallel on a conveyor belt, with their tips directed toward a set of pressing rollers that use mechanical force to keep them straight and stable. The conveyor then feeds the leaves into the decortication machine, where high-speed rotating drums crush the leaf pulp and separate the long fibers inside. The pulp and plant juice are expelled at the decortication chamber, while the raw fibers continue forward, retaining their full length. A standard production line can process 20 tons of leaves per hour, yet the output is highly selective. Only about 4% of the leaf's weight becomes usable fiber. The raw fibers then pass through a continuous washing system to remove sap and plant residues, before undergoing preliminary combing to separate and straighten the strands. Within just a few minutes, a fresh green leaf is transformed into raw fibers, ready for the next stages of processing. After washing and preliminary combing, sisal fibers enter the drying stage, a critical step that determines both color and durability. The fibers are spread out or hung evenly on drying racks, ensuring they do not overlap so moisture can evaporate uniformly. In major production regions such as Tanzania and Brazil, sisal is typically sun-dried, where ambient temperatures average around 30 to 35 degrees Celsius. The drying process usually lasts 2 to 3 days, until the moisture content of the fibers drops below 12%, a safe level for storage and further processing. If drying is insufficient, the fibers may darken, lose strength, and become more susceptible to mold. After drying to the required standard, sisal fibers are collected directly at the drying yard, the moment when the fiber's final form first becomes clearly visible. The fibers are removed from the racks and carefully recombed to eliminate short strands, sand, and remaining impurities. They are then graded by length, color, and uniformity. From over 1 ton of fresh leaves, only around 40 kilograms of usable fiber remain, bundled into 20 to 25 kilogram bales. This is the critical stage where raw mass is refined into true value. After being delivered to the factory, sisal fibers are fed into an industrial rotary drum combing machine to clean and even out the fibers. Inside the machine, steel rollers fitted with metal teeth rotate continuously at a speed of approximately 400 revolutions per minute, pulling and aligning the fibers in a fixed direction. This process straightens the fibers, separates tangled bundles, and removes short fibers and residual debris. The spacing between the rollers is precisely calibrated to just a few millimeters, sufficient to clean the fibers thoroughly without breaking the long strands. Immediately after combing, the sisal fibers are transferred directly to a hydraulic baling press. Here, the fibers are compressed into standard bales weighing approximately 25 kilograms, reducing volume and stabilizing their shape. The baling stage marks the end of fiber processing within the factory, transforming loose sisal fibers into a complete raw material unit ready for the next stage of spinning. At the spinning mill, sisal fiber is not fed directly into the twisting process. The first step is fiber alignment. Bundles of fiber are separated, stretched, and arranged parallel along a single axis. This step eliminates the natural misalignment of plant fibers, the primary cause of fiber breakage if twisting begins too early. Once the fibers are aligned in the same direction, primary twisting begins. At this stage, the fibers are lightly twisted at a density of around 100 twists per meter, just enough to form a stable single yarn. The goal is not strength, but to prevent the fiber from separating during further processing. Next, the single yarns are plied and subjected to secondary twisting. Depending on the intended application, sisal may be spun into 2-ply or 3-ply yarns. Increased twist density locks the fibers tightly together, creating a structure capable of bearing load and resisting abrasion. Even a small deviation in twist level can reduce the fiber's service life in real-world use by up to 40%. At the end of the spinning process, sisal yarn is twist set and strength tested, then graded and sent on to subsequent stages, most commonly rope making. And now, sisal yarn enters the rope-making stage, where a single strand is transformed into a fully load-bearing structure. The process begins with strand assembling. Multiple spun yarns are fed in parallel into the machine and held under controlled tension before moving into the next twisting phase. This is followed by cable twisting. The strands are twisted in the opposite direction of the original spin, balancing internal forces and preventing the rope from unwinding under load. Depending on the design, sisal ropes typically consist of 3 strands, each made up of dozens of finer yarns. This multi-layered structure allows the rope to distribute stress evenly and improves resistance to abrasion during use. Once the required twist is achieved, the rope is set and continuously straightened over lengths of up to 200 meters in a single production run. Even minor deviations during twisting can create localized weak points. For this reason, finished ropes undergo load testing with tensile strength capable of exceeding 1 ton before being cut, coiled, and packaged. At this point, Sisal completes its journey from a plant-based fiber to a reliable load-bearing tool used across everyday life and industry. The journey of Lotus fiber follows a completely different path, more meticulous, more labor-intensive, and far more delicate. Lotus stems are typically harvested between May and August, when the plant is at its peak growth and the fiber content inside the stem is at its optimal condition. The ideal time for harvesting is early in the morning, when the stems are still fresh, rich in natural sap, and have not yet been dried by the sun. If harvested at midday or in the afternoon, the fibers inside quickly lose their elasticity, making them extremely difficult to extract. After harvesting, the lotus stems are washed thoroughly before any further processing begins, in order to remove mud and impurities, and to keep the stems fresh so the fibers are not damaged. The extraction of lotus fiber must be carried out within 6 hours after harvesting, while the lotus stems are still fresh and rich in natural sap. First, the stems are cut into short sections of about 20 centimeters, a length suitable for hand processing. Each section is then gently broken open, exposing the fine fibers hidden inside the stem. From each section, the artisan typically pulls out around 10 extremely delicate fibers, almost transparent and very easy to break. These fibers are too short to be used individually, so they are joined together by hand, lightly twisted between the fingertips to form a continuous thread. Throughout the process, the fibers are kept slightly damp with water, which helps maintain flexibility and prevents breakage. The entire operation is slow and entirely manual. On average, a skilled worker can extract about 200 meters of lotus fiber in a single day. If the stems dry out or the movements become too forceful, the fibers quickly become unusable. After spinning is completed, the lotus fiber enters the winding stage, the final step before weaving. At this stage, the fiber is guided through a winding machine to control both tension and direction. The machine keeps the fiber under just enough tension, preventing sagging, misalignment, or overlapping as it is wound. The winding process moves very slowly, as lotus fiber is extremely fine and fragile. Any sudden increase in tension can cause the fiber to break at its weakest point. During a stable run, the fiber can be wound continuously into a spool of approximately 150 meters, sufficient for use as warp yarn on a traditional loom. If the fiber is unevenly distributed, or the spool becomes misaligned, the entire roll cannot be used for weaving. For this reason, the artisan must constantly observe the process, adjusting the hand crank and machine speed. It is at this stage that loose lotus fibers are transformed into ordered spools, ready to enter the demanding process of lotus silk weaving. When the lotus yarn spools are ready, the process of weaving a lotus silk scarf begins with loom setup. The lotus yarn is stretched as warp threads on a traditional hand loom, one strand at a time, with tension carefully calibrated to keep the fabric surface even. If even a single thread is misaligned, the warp can break during weaving. During weaving, the artisan opens the heddles to separate the warp threads, passes the weft yarn through the opening, and then beats very gently to secure each row. Every movement is slow and deliberate, as lotus fiber is extremely fine and brittle. In a single working day, the weaver may need to stop hundreds of times to repair broken warp threads, something that rarely occurs when weaving silk from silkworms. Each repair requires precise tension, otherwise the fabric surface will be flawed. At this pace, completing one lotus silk scarf typically takes around 7 consecutive days, with less than 1 meter of fabric woven per day. This slow, high-risk process, entirely dependent on skilled craftsmanship, is what drives the price of a lotus silk scarf to between $300 and over $1,000 USD, making it a textile that is nearly impossible to mass produce. If you look at the bell pepper market straightforwardly, the picture is quite clear. China grows the most in the world. Mexico is the major supplier for the United States, and Spain functions as the key distribution hub for all of Europe. These 3 regions link together to form a massive flow of trade, and it's this connection that underpins a bell pepper market worth nearly $10 billion. In supermarkets, many people assume red peppers are the premium choice because they take longer to ripen and therefore cost more. But from a cooking perspective, each color has its own purpose. Green peppers are crisp with a light sharpness, great for stir-fry and Asian dishes. Red peppers are sweeter and softer, ideal for salads and grilling. And yellow or orange peppers sit somewhere in the middle, easy to use across many types of dishes. So the question isn't which color is superior, it's which one fits the dish you're making. And the idea that light can change a pepper's color? That's completely true. In greenhouses, growers can speed up or slow down the color-changing process simply by adjusting the type or intensity of lighting. It's a very common technique in modern agriculture, but one that most people would never notice just by looking at a multicolored pepper in the supermarket. The most critical factor determining the quality of bell peppers is the timing of harvest. Within just 7 to 14 days, they can shift from green to red or yellow. Pick them too early and they lack flavor and color. Weave them just a few days too long and their crispness and market value drop noticeably. In other words, harvesting bell peppers is genuinely a race against time. Early autumn is when the peppers reach their fullest shape and strongest coloring. And it's also when the season officially begins. Across fields spanning dozens of hectares, specialized harvesters start up simultaneously, producing the signature hum of modern agriculture. They move slowly but steadily, sliding harvesting arms into each plant, lifting the entire stem, and shaking it so the peppers fall onto the conveyor belt. From there, the stream of peppers passes through rotating brushes, suction fans, and continuous sorting systems that remove leaves, soil, and defective fruit, leaving only the high-quality peppers to drop neatly into the collection bins. Thanks to these machines, productivity has changed completely. A single harvester can replace hundreds of workers, and what once took a month to gather can now be collected in just a few days. At many large farms, weekly harvest volumes can exceed 300 tons, a figure nearly impossible to achieve with manual labor alone. This isn't just a story about faster harvesting. It's a clear example of how technology is reshaping agriculture. Fewer people, less time, and far more output, all while keeping product quality consistent. When grown in open fields, bell peppers can only be harvested during a few warm and dry months. But to sustain an industry that consumes millions of tons each year, growers have to extend the production season. The solution lies in greenhouses, where light, temperature, and humidity are controlled down to the smallest detail, allowing peppers to be harvested year-round. In this environment, the harvesting process also changes. Workers don't pull or shake the plants as they would outdoors. Instead, they use pruning shears to cut each pepper individually to keep the stem intact, because even a slight bruise on the stem can lower the fruit's grade during sorting. The freshly cut peppers are placed on plastic trays mounted on small electric carts, vehicles that can run continuously between rows barely 80 centimeters wide without breaking branches or scratching the fruit. Once the trays are full, the carts unload the peppers into a small trailer hitched to a tractor. Its low chassis allows quick loading, its tight turning wheels help it maneuver easily in confined spaces, and safety sensors reduce collisions. Crucial because even a small scratch can make a pepper deteriorate 30 to 40% faster. When an entire greenhouse block is finished, a line of carts heads straight to the processing area, where facilities can receive anywhere from tens to over 200 tons of fresh peppers per day, depending on the size of the farm. This is the key link that keeps the bell pepper supply stable throughout the year, regardless of weather or season. As soon as the peppers reach the collection point, massive hydraulic machines immediately lift the crates into the processing line. With a single tilt, an entire crate of bell peppers pours onto the conveyor like a waterfall. But instead of bruising, cushioned chutes and soft conveyor belts absorb the impact, keeping every pepper intact. Thanks to a precisely timed speed control system, up to 2,000 crates can be handled smoothly each day, an impressive starting point for the industrial journey of bell peppers. The first step in the industrial process is cleaning. Crates of bell peppers move into an automated washing system, rolling across massive horizontal brushes that strip away layers of soil as if they were never there. Immediately after, they meet a blast of high-pressure water combined with strong airflow, washing and drying the peppers in just a fraction of a second. After cleaning, bell peppers move into the most critical stage of the entire production line, sorting, where the commercial fate of each pepper is decided. On the system of rubber-coated rollers, the peppers rotate, not just to move forward, but to expose every part of their surface, including areas that are usually hidden, such as the bottom, the stem, and the grooves between the lobes. Above them, a multi-angle camera system captures 60 to 120 images per pepper, combined with high-precision 3D sensors and color sensors. Together, they record the pepper's size, shape, color uniformity, surface gloss, physiological ripeness, and any surface damage as small as 0.2 millimeters. Right after the scanning zone, each pepper enters an individual tray. a structure specifically designed for difficult produce like bell peppers, which have irregular shapes and thin, easily scratched skins. Each tray holds exactly one pepper, equipped with an ultra-sensitive scale with an accuracy margin under ±1 gram, along with an auxiliary rotation mechanism to complete any missing angles of data before the system makes its grading decision. In practice, if a sorting line can accurately grade bell peppers, it can handle almost any other challenging fruit or vegetable. No two bell peppers look alike. Their lobes are uneven, their shapes asymmetrical, and their value depends heavily on the perfection of their surface. This is why the market has more machines dedicated specifically to bell peppers than to apples, tomatoes, or mangoes, even though those crops sometimes have much higher overall production volumes. On the market, most bell peppers are sold whole in plastic bags. In the United States alone, the number exceeds 5 billion fresh peppers every year, meaning billions of those familiar bags you see on store shelves. But few people realize this isn't just a convenient packaging method, it's also a vivid demonstration of consumer psychology at work. Red and yellow peppers trigger appetite, while green suggests freshness. When all three colors sit next to one another, they create an irresistible visual pull, a mix of contrast and harmony that distracts you, makes you hesitate, and ultimately makes you far more likely to add to cart than you planned. However, plastic bags are only used for retail. At industrial scale, where demand is measured in tons rather than in bags, bell peppers are packed into cardboard cartons. Each box weighs 5 to 10 kilograms and holds 30 to 80 peppers, meeting the standards required for storage and long-distance transport. From there, fleets of refrigerated trucks line up and leave the processing plant, carrying bell peppers to supermarkets, wholesale markets, and even high-end restaurants across the country. After the sorting stage, the bell peppers are moved to the stem and core removal area. Here, workers use specialized tools, usually a cylindrical coring knife or a tube-shaped cutter with a diameter of about 25 millimeters, to trim the stem and clean out the entire core. Each worker can process an average of 400 peppers per hour. After being cored, the bell peppers are lightly blanched at 90 to 95 degrees Celsius for 2 to 4 minutes to soften the flesh, lock in color, and reduce the microbial load before canning. However, depending on the product line, the peppers may also be roasted instead of blanched. Roasting adds a natural smoky aroma and helps loosen the thin outer skin, making it easier to peel. After roasting and rapid cooling, workers use gloved hands to remove the loosened skin and trim off any charred spots, or on larger production lines, rotating drums and strong air jets handle the peeling automatically. Roasted peppers stay tender but hold their structure well, making them ideal for richer, more flavorful canned varieties. Whether blanched or roasted, the peppers are immediately transferred to the filling hopper and packed into sterilized tin cans. A 1.5 to 2% brine solution, heated to 80 to 85 degrees Celsius, is added to remove air bubbles and create a stable preservation environment. The cans are then sealed using a double or triptyseam system, ensuring an airtight closure before sterilization. In the final stage, the cans enter a retort unit and are sterilized at 121 degrees Celsius for 20 to 30 minutes, eliminating all harmful microorganisms, while preserving the pepper's natural crunch, color, and structure. Not everyone realizes it, but the thick skin and hollow cavity of bell peppers seem almost purpose-built for stuffing. And surprisingly, stuffed bell peppers were also one of Princess Diana's favorite dishes, so much so that she could eat them 2 to 3 times a week without ever getting tired of them. According to former royal chef Darren McGrady, her preferred version was bell peppers stuffed with zucchini, mushrooms, and rice, topped with mozzarella and parmesan, then finished with a smoky tomato sauce. Under heat, the pepper softens and turns sweet, soaking up the sauce, while the filling becomes firm and flavorful. The gentle sweetness of the vegetables blends with the salty richness of the cheese, creating a dish that is both refined and comforting, the kind of flavor that warms anyone from the inside out. When tossed in a hot pan, the crisp sweetness of bell peppers stays intact, while releasing their signature aroma. Just a few slices can instantly brighten the entire dish with color. They can be stir-fried with chicken, beef, pork, or simply with onions and mushrooms. And each combination brings out a different flavor profile. Chicken with bell peppers is light and delicate. Beef makes the dish richer and more aromatic, while a vegetarian stir-fry keeps the pure sweetness of the vegetables. It's one of the quickest ways to create a dish that's easy to make, visually appealing, and nutritionally balanced.